CHEM200L. This is the pre-lab lecture for experiment 5 on April 22nd. So as you can see, April 22nd, that's the pre-lab data observations that are due for experiment 5. I mentioned this in the last video, but that experiment 4 post-lab isn't due till the 27th, but I hope you've already finished it. I hope that's off your to-do list, and now you can focus on 5. You can see the post-lab for 5 is not due until May 4th. The reason I'm telling you this is now we're in this routine of a lab every week, basically. Okay, so the workload can really build up if you're not on top of things and you're not organized. So I really encourage you, stay on top of it, come to office hours, see me so we can talk where you're at, what you need to do. Another check-in is exam 2. This exam will be on Canvas, covering activities 7 through 12, experiments 3 through 5. So I need to make sure after that quiz that you're comfortable using Canvas and ready to go for the exam on the 27th. Then it doesn't stop, people. Experiment 6, April 29th, and then not long after that is the withdrawal date if you're considering that. So what we need to talk about for experiment 5 is reactions. You're going to see some great chemical reactions in the video. This is one of the favorite labs of students when they've done on campus. Some really great, interesting chemistry. Going to talk how those reactions lead to completion. Then we're going to be able to evaluate how good was the system, how good was your yield, and that has to do with considering limiting reactants. And then experiment 5 on lab archives, like experiment 3 and 4. So schedule experiment 5 and the next week exam and experiment 6. So quick refresher, we haven't talked about this in lecture yet, but you may recall from Chem 152, you could classify chemical reactions as either what atoms do over here on the left, how they rearrange, or actually the chemistry, okay? That's over here, what happens chemically. So what I want to remind you is combination. That's two substances, and they come together and form one substance. Well, then you can imagine or remember decomposition is just the opposite of that. That breaks apart into two things. And single displacement, one thing gets pushed out. So here, if we talk about AB being an ionic compound, then the C knocks out the metal. So that goes CB, C's now in the cation, and A gets pushed out. Double displacement, it's a big switch for both of them. So just keep in mind the notation. I'm making the cation go with the anion of the other, so that's AD, and the cation of the second one, C, goes with B. So those are rearrangement of atoms or rearrangement of particles, one way to classify. The other is the chemistry, okay? Combustion engine, octane, that's combining with oxygen, and that gets us CO2 and water. So that's a combustion reaction. The oxidation reduction we'll spend some time talking about, but really in Chem 201 you have a whole chapter on oxidation reduction reactions. That's where I save the chemistry on oxidation reduction. But a nice classic example of that is sodium, elemental sodium, so there's no charge, and we react that with chlorine. That's also no charge, and you can see these are elements. And the elements combine and form an ionic compound. So now we have ions, Na plus, Cl minus, and the reason we have those is because sodium lost electron and chlorine gained an electron. So that's an oxidation reduction reaction. Precipitation is when you see like silver chloride forms out of two solutions. So silver nitrate, sodium chloride, that forms silver chloride. So that's a precipitation reaction. Neutralization is an acid and a base. So that's HCl, and Then we can have any kind of base here, so I'm putting in sodium hydroxide. And acid-base, we'll talk about this in lecture as well. Acid-base equals a salt and water. And the salt, it just means any ionic compound. And in this case, the ionic compound is NaCl. And this is the nice one, you got water. Kind of a give me answer. Gas evolution, you could form bubbles. We saw that on campus with hydrogen gas. We saw that with H2S. That was very memorable. CO2 gas. So gas evolution is when two aqueous solutions are reacted and a gas bubbles out of that. Okay, so that reminds me of what we want to talk about here in terms of completion. Okay. So what you're going to find in this experiment, if you were doing it in our lab, it would be pretty straightforward to see this. But as you're watching it, I really want to encourage you to think about it. This is happening in one beaker. So if you have something that goes out of the beaker, like, or goes out of the solution, excuse me, like a solid, if a solid forms, that drives the reaction to completion because it's out of solution. If you have a gas that forms, that drives it to completion, that goes out of solution. So what we mean by this completion is some reactions, if we consider A going to B, won't actually go 100% to B. Maybe it'll go 70% or 80%. But if we want to drive it to completion, it happens with reactions that go out of solution, solids, gases. So you want to look at the chemical reactions that you're going to do and observe in experiment 5 and see what's making this go to completion. Because really, this experiment, you start with copper, you should be able to end up with 100% of that copper. Okay, of course it's experimental error, things happen, but this is the idea. These are driven reactions to completion. You should be able to get yield, 100% yield. So that's how we evaluate this completion, is we calculate the percent yield. So if we take a look here, I just wanted to put an example up of a limiting reactant and percent yield problem. So if you want to do this one, you can go ahead and pause the video and start doing your calculations of this magnesium-oxygen reaction to form magnesium oxide. If we take a look here, we'll see that limiting reactant problems, you may recall, you have one reactant, you have another reactant, and you do two stoichiometry problems. Okay? You do these two stoichiometry problems, and then you compare, and you realize that this 2.11 is bigger, so the least amount of product is your theoretical yield. Okay? And you could stop here at moles like they did, and then convert it to grams, and get your theoretical yield in grams. So what we're interested in is, well, if that's the theoretical yield, how good was this reaction if they collected 55.9. So it's really important to be able to identify what's the actual yield, how do you calculate the percent yield, what's the theoretical yield here in terms of moles or grams. So the next step would take the actual yield, 55.9, divided by the theoretical yield, 70.5, and you get 79.3 here for percent yield. It depends on the chemistry, depends on the reactions. Some reactions, like today, it should be around 100%. I did some reactions in graduate school. If I got 20 or 30%, I was happy. So it just depends on the chemistry of what these yields can really mean. So a couple things to note for this experiment, we're going to see on the next slide. You are just looking at one reactant. Everything else is in excess. So you don't have to do any calculations on, well, which one's excess, which one's the limiting. You are doing one measurement of a reactant with precision using the decimal places that we normally do. So that's the one that you're basing it on. So a couple of notes to be aware of. The video, I think, is really reflective of what we do on campus. So make observations from every experiment. And this is some great chemistry, really interesting. So really encourage you to make good observations here. One thing I do want to note is that their reaction 1 starts with copper solid. Okay, so they have copper solid and they add nitric acid and they get copper nitrate. Well, what we do at Miramar in lab is we actually just start with the copper nitrate, hydrate, and then every other reaction is exactly the same. Okay, so just note, reaction 1 will not be in your lab packet. I will not give you the data for reaction 1. What I'm going to give you the data for is right here, 1.501 grams of the copper nitrate trihydrate. That means you need to use the molar mass of the whole substance, because that's what you weighed out. And then at the end, when the copper is recovered in the video, you can say, well, we recovered 0.347 grams of copper. So now you need to think about this number. What do I do with that number? And this number, what is this number? How do I use that in a calculation? That's what you're expected to do for experiment 5. When you think about these calculations for theoretical yield, you know, there's lots of reactions there. What are the mole ratios? Well, all we care about is the copper. Okay, so just think about the mole ratios of the copper from one reaction to the other. And as I mentioned, everything else is in excess, so you can just assume the volumes are all similar to what's done in the video of all these reactions. So you don't need that data. This is the key data that you need. So again, I encourage you to come to office hours if you want to talk about this experiment, and enjoy.